Okay, let's try and understand effect of pressure on solubility. Now prior to getting into it, let's understand some conversion factors. 1 bar corresponds to 1 atmosphere. Bar and atmosphere, same value. That corresponds to 750 torr and 14.5 psi. Psi is pounds per square inch. Alright. Again, another important conversion factor as we deal all the numericals in SI unit unless mentioned otherwise. This is one conversion factor. Then this is what we use for SI unit, meter cube, right? So 1 decimeter cube is 10 raised to minus 3 meter cube. So these are some of the conversion factors, very significant for your numericals. Okay, now let's get back into effect of pressure on solubility. It's anybody's guess that solubility of gas increases with pressure. But this relationship was penned down by Henry. So Henry's law states that solubility is directly proportional to pressure. Alright, and we also know when proportionality sign goes, we get one constant, and that constant is K subscript H. Obviously H is for Henry and P is pressure. Alright, so this is Henry's proportionality constant. Alright, so S is equal to KH into P. H is subscript. Alright, now solubility, unit of solubility, very much required. Unit of S would be moles per liter, and moles obviously I have mentioned in my other video where mole is what? It's mass upon molar mass. That is what is moles. Alright, and what is the unit of pressure that we use here? It is bar. It is bar that we use. Alright, so suppose if I intend to get unit for KH, it would be S over P. This P would come below S, solubility and pressure. Alright, so solubility we know unit is mole per liter, and below that again another pressure is there. Now pressure unit is bar, so it would be bar inverse. So unit for Henry's law constant is moles per liter per bar. Alright, so this is one thing which we have got to keep in mind. Now apart from this, let's get into an example, an interesting example rather, for relationship of solubility of gas and pressure. Alright, so let's come to this bottle. This is bottle with aerated drinks. So I have not filled in aerated drinks here. Okay, let me fill it up. Okay, so this is all those aerated drinks that you have, that you enjoy. Alright, now these have effervescence within it, so you know that. Now suppose if I take any drink, now these drinks are all aerated. Aerated, what do you understand by aerated? Aerated is this has got liquid which has been pressurized with carbon dioxide gas. Alright, now so pressurized and closed under pressure, so as a result of which the entire liquid has sufficient quantity of carbon dioxide gas in it. Alright, so if I open up the cork, alright, so as I did here, so what do I observe? I find that all this fizz, whatever is there, effervescence, whichever is there, it just comes out of the bottle and then it becomes stable. Then there we see no more effervescence coming out after some time. Now, but I want effervescence again to come out. What do? I just take the bottle, shake it thoroughly well. So on doing that, what happens is, on shaking the bottle thoroughly well, what happens is, we again see some effervescence coming out. Why does it come out? It comes out owing to friction generated when I'm shaking the bottle, the lamellar layer of liquid, whichever is there in bottle, friction is generated in between those lamellar layer of liquids. And by friction, we know heat is generated. Now, since heat is generated, the gas, whatever remnant gas in the bottle expands, and as a result of which it again comes out. So, first we open the bottle. Since the pressure was released, so effervescence also released. Then we shook the bottle, heat was generated, owing to which gas expanded, heat was generated owing to friction of lamellar layers of liquid, and gas expanded, and as a result of which volume of gas expanded, as a result of which again we saw some effervescence. Now again I want some more effervescence. What do? I put some salt into it. As soon as I put some salt, of course it has to be soluble in the solution, in the liquid. So I put some salt, or I put lemon. As soon as I do, or some citric acid or something I put which is soluble into this liquid. So what happens? I again see effervescence. Now why do I see effervescence? I see effervescence owing to displacement reaction. Now this salt, now suppose if I put NaCl dissolves into this liquid and displaces carbon dioxide. Now keep one thing in mind, carbon dioxide goes into water. Now carbon dioxide reacts with water to form H2CO3, carbonic acid, highly unstable. So I put backward forward, highly unstable. So as soon as you put in sodium chloride, that goes into water and displaces carbon dioxide out to generate effervescence. So got to keep in mind, first depressurization generated effervescence, vigorous shaking generated effervescence owing to heat, expansion of gas theory, and in third case on addition of some salt like NaCl which goes into water and displaces carbon dioxide out, so we get effervescence. Alright, interesting, isn't it?